So I just noticed that the previous podcast I recorded through the computer microphone instead of the headset, even though I had the headset on, so it sounds a little echoey, but it's clear, so I'm not going to re-record it. 20 minutes almost. So anyway, let's move on to now looking at some schematic of the most fundamental physical processes that are involved in the interseasonal oscillations. These are the kind of things we will look in the figure that's much more evocative in the next slide. So convection interacting with dynamics is acronymed here as CID. So the CID processes are marked by marbled shadings in the figure we will look at, which comprises the collective effects of convective heating. Diabatic heating is an important aspect of ISO, the fundamental process which determines the waves going out, the dynamic feedback with the convergence, moisture, and so on. Maybe I'll do the laser again. I got forced into this laser business now. Low frequency equatorial Kelvin and Rossby waves, so they are not free waves as we will see, and we have already mentioned several times, so they move slower than the free waves. Planetary boundary layer dynamics, which is the link between the enthalpy flux from the ocean or land into the free troposphere. So you have to go through the boundary layer dynamics, which is critical for frictional convergence, instability, and so on. Surface heat and momentum exchanges through WISHY, wind-induced surface heat exchange, with the lower boundary, which is part of the heat flux and energy coming into the boundary layer and the atmosphere. Moisture feedback between convection and its dynamics. So we talked about wave sisk and so on, where warmer sea surface temperatures, the enthalpy fluxes, rising motions with moisture are going to drive convection and the circulation dynamics associated with it. Upscale momentum and heat transfer. So when you take the seasonal mean as the background state and then split the equations into intraseasonal timescales as perturbations on the background state, and then you have higher spatial scale or temporal scale processes which are, let's say, synoptic scale. So typically you can think of U, let's say zonal wind, as U bar, which is the seasonal mean, U prime, which is the intraseasonal time scale, and then U double prime, which is higher wave number, higher frequency, higher spatial scale, or smaller spatial scale processes. So the upscale momentum and heat transfer is basically either from intraseasonal time scales into seasonal time scales, what I refer to as low frequency rectification before, or even from the synoptic scales into the intraseasonal time scale. When you do momentum budget and so on, you get to see how those processes work. Okay, so these feedback processes integrate the following mechanisms, which we will go through in the following section. Convection wave convergence feedback, frictional moisture convergence feedback that I just mentioned, evaporation wind feedback, which is similar to WISHY, moisture feedback, which is the convection moisture dynamics that's going to create dynamic responses, and mesosynoptic scale feedbacks, where you have larger scale and convective scale interactions that are going to amplify the responses at ISO timescales, which is our main focus here. So convection interacting with dynamics, or CID, is considered essential for understanding the basic internal dynamics of the MJO, and not so much looked at in the mesos, but you can be sure that they are also important there. So here is a figure. So these are the numbers which will be discussed one by one in the sections that follow. So you have land-sea distribution. This is of course important for the monsoon, but also for the MJOs propagating eastward, the maritime continent, the orography there, the land-sea contrast, and all those things are very important for whether the the MJOs transition across the maritime continent, they are detoured southward or they get stalled on the eastern Indian Ocean side and so on. Background circulation for mesos, it's obviously the monsoon vertical shear that we talked about and we will talk about again. And of course there are climatological SSTs, which are the source of water vapor variability or variation. So if we go to process number 1 here, the background circulation, monsoon, vertical shear and so on generate low frequency equatorial waves, which we'll mention again in a bit. That is related to convective latent heating, so the diabatic heating sends off waves, equatorial Kelvin and Rossby waves that we talked about, and that is going to be also depending on Vichy, the wind-induced surface heat exchange, affecting the boundary layer dynamics, and that of course affects the convective latent heating. So you get the connection from 1, 2 feeding into 3, and then you have 4 happening here, so low frequency equatorial waves and cloud radiation processes and feedbacks. So cloud shortwave reflection and absorption, outgoing long wave combined with Vichy from the bottom and the boundary layer dynamics are going to determine the instabilities, and that's also going to affect the ocean mixed layer. Then you can jump to 5, where you are looking now at the interaction between convective heating and boundary layer dynamics affecting the water vapor variation in addition to the SSTs. So how the convergence and rising motions, so convective heating and the feedback and boundary layer dynamics are going to affect water vapor variation in addition to SSTs. Which also is related to low frequency equatorial waves and mesosynoptic systems, or the multi-scale systems. So even though we are jumping around, they are all related to each other and add up to the MJO dynamics and its interactions with the lower frequencies and the higher frequencies, so synoptic systems and mesoscale systems. So there is 7 again relating monsoon vertical shear to low frequency equatorial waves, and finally the ocean mix layer affecting the boundary layer dynamics as well. We talked about whether the balances are nearly one-dimensional with the heat fluxes explaining it, or whether ocean mixed layer processes like advection in the horizontal, vertical advection, mixing and vertical entrainment of the thermocline waters into the surface, and the barrier layer processes as well affect the boundary layer dynamics. Okay, so those are kind of the fundamental processes that we will look at. We will first introduce ourselves to a model that's going to be used to go through these processes. It's a 2.5 layer model built by Bin Wang and his group. So we will go through the equations to see how the model works and what kind of assumptions are made in building the model, and how it couples the boundary layer and the various simplifications made to understand the processes. So in general, you have the full coupled ocean, atmosphere, land model, sometimes even the vegetation and carbon cycle model. And one way of approaching MJO's interseasonal oscillations is to explore these fundamental processes in the full system being simulated, or you make some assumptions considering these are the tropics, making some linearizations, shallow water equations and so on, and then understand the processes then that you can go back and look at in the full GCNs to see how the full dynamics captures these processes. So process understanding is sometimes easier with the simplified models, which is where we will start in the next podcast. Okay?